this talk is going to summarize the results of these two recent papers, one of which was joint with Thomas Fritz, Nick Kavanagh, and Adam Mameliti, and then the second did not have Thomas involved. Okay, so some admissions at the start. I guess I'm coming from a combinatorics background, so if I ever say Hadamard matrix, I will mean real Hadamard matrix, like the real Hadamard matrix that we had here. I see it's now reduced to an order 1 real Hadamard matrix, but anyway, that's what I mean by Hadamard matrix. And if I ever say orthogonal, it will be a combinatorial meaning of the word orthogonal, not an algebraic meaning of the word orthogonal. And the other thing I want to say at the start is if I ever use the letter n, it will be the order of my squares. Okay, so what I'm talking about. Frequency square is just a square matrix where each row and column is a permutation of the same multi-set of symbols. So anyone who knows me knows that I love thinking about the case where S is actually a set, so everything has multiplicity 1, and that's what gives you a Latin square. But actually, what I'm going to talk about today is the opposite extreme to that, although many of the questions that I'm going to consider are motivated by comparisons with the Latin square case and by work that's been done in that case. So what am I talking about? I'm talking about balanced binary frequency squares. So binary means my symbols are just zeros and ones. Balanced means there's as many zeros as there are ones. So necessarily my n will always be even, and every row and column will have the same number of zeros as one. So very simple matrix. And we do know stuff about the unbalanced case and about more general symbol sets, but I'm going to stick to this very simple case just for, you know, it's late in the day. We don't want to have to work too hard, right? So let's just look at this case. And my notion of orthogonality means superimpose the two matrices and then look at the ordered pairs that you get. There are 4 possible ordered pairs, 0, 0, 0, 1, 1, 0, and 1, 1. And we have the same number of zeros and same number of ones, so it's plausible that we get the same number of each of these pairs. And if we do, I will say that the squares are orthogonal. So very simple example to make sure we're all on the same page. Here's 2 binary balanced frequency squares, put them together, and I see 4 times 0, 0, 4 times 1, 1, 4 times 0, 1, and 4 times 1, 0. Okay, so that's what I'm talking about. And obviously you can also get these from Latin squares if you choose to take your Latin squares. If you have mutually orthogonal Latin squares and you take them mod 2, then you'll get mutually orthogonal binary frequency squares. You'll lose a lot of information when you do that. So this is not what Ronan was doing. He's not reducing the, well, I am reducing the symbol set, but I'm losing a lot if I do that. If you want to retain all the information, then you'll need some kind of affine design in order to expand your set of these things, but I don't want to talk about that. Okay, so so then we have a concept of mutually orthogonal frequency squares, or MOFs, which apparently is a rude word in South African, but I hope there's not any South Africans in the room. So that's where you have a set of these frequency squares, and each pair is orthogonal in the sense I just defined. And if you have n-1 squared squares in your set, that is called a complete set. And the reason for the terminology is there's an easy dimension argument that says you can't get anything bigger. This was originally proved by Hediat et al. In 1975. Their proof was pretty opaque to me, but here's a gist of a very simple proof that makes sense to my wee brain. So you can think of these squares living in a Z2 dimensional vector space of order n squared, and then look at the indicator functions for the rows. You've got n of those. I'm going to build a set of independent vectors. So take all of the rows, take all of the columns except one, and then take all of the places that ones occur in your matrices. All those vectors are linearly independent in this n squared dimensional space. So you better not have more than n-1 squared symbols to go with the 2 n-1 lines that you started with. Okay, so very simple. And And it turns out, and my justification for talking in this conference about this subject is that if you give me a Hadamard matrix of order n, I can build a complete set of MOFs of order n. And this result goes back to Federer in 1977, I guess a bit before he started playing professional tennis. But his proof was very opaque again. I'm going to give you a one-line construction that does this. And the proof is not many more lines than what I've put on the slide. But before I do that, I want to also say that we got more out of this result. So actually, if you give me a Hadamard matrix of order n, I can give you really a lot of not equivalent complete sets of MOFs of that order. So from this construction, which I'm about to give you, Federer would give you one complete set of MOFs. We can take that complete set of MOFs and twist it around in various ways, still remaining as a complete set of MOFs. So keyword here is trades, as Horik is nodding, and create things which are not isomorphic, but still have the right properties. Okay, so what's the construction? You just take your Hadamard matrix, normalize the first row, so it's all ones, and then your remaining rows are sort of balanced orthogonal plus one minus one matrix vectors, and then take all of the rank one products that you get from these rows. And it's really that simple. That will give you, well, so I threw one row away. I've got n minus one rows left. I can take any pair of them, not necessarily distinct. So I've got n minus one squared matrices, and obviously that would give me plus one minus one matrices, but then I'd change all the minus ones to zeros to fit with my definition, and it's really that simple. Okay, and you could all prove that this works in a minute. Okay, so we then muck around with that and get lots of things which are not rank one matrices, but still complete sets. There's an interesting other theorem that we proved, which is there are no complete sets. So that works for any order which is a multiple of 4. My n is necessarily even. What about 2 mod 4? Well, there's no complete sets in that case. And this is not just a case of saying there's no Hadamard matrices of that order. You need to do something else. Actually, we proved that if there was a complete set, there's a particular resolvable design which you can show doesn't exist. And so there's no complete sets in this case, which is an interesting contrast to the Latin square case, because this is a big open problem for Latin squares, whether you can achieve the obvious bound for 2 mod 4. But here it's very simple to show you can't. And I should also say, if you're interested in these things with more than 2 symbols, you just have to divide the n minus 1 squared by m minus 1 if you have m symbols. And it's the same argument that I gave you. Very easy to see. And so that sort of generalizes down to the Latin square case. Yep, question? Yep. Correct. Yes. Yeah, it only goes one way. I mean, I guess if probably, I don't even know for sure, but probably if you have a complete set which are all rank 1 matrices, then you can get back to a Hadamard matrix. I don't know that for sure, but there are many sets which are not. So yeah, it doesn't go the other way. Okay, so question that's been talked about a lot for Latin squares, and I have investigated in that area, is the idea of a maximal set. So a set of MOFs is maximal if you can't extend it, you can't add another thing which is orthogonal to everything you have already. Obviously, if you have a complete set, it's going to be maximal by definition. Actually, for order 4, surprisingly, the converse holds. So for order 4, there's nothing which is non-trivially maximal. But for order 6, things are very different. So for order 6, if you make a bad choice, you can get stuck straight away with the first square. You might be able to go no further. You can also get stuck at 5, 6, 7, 8, 9, 10, up to 15, and at 17. And this is already surprising to me, because obviously, famously, there's only one orthogonal Latin square. I mean, there's not a pair of orthogonal Latin squares of order 6. We can get 17 orthogonal MOFs, which is a lot closer to the complete. So complete set would be 25. So this is sort of like finding 4 MUBs of order 6, I guess. Yeah, we get a lot further than I expected to. And it's also interesting what happens down the bottom, which I will explain later in the talk, why there's this possibility getting stuck at the start, but then there's a gap, which is also somewhat interesting and will come up later. So towards that end, I can tell you that there is a maximal single square if and only if your order is 2 mod 4, and I will give you the construction in a few slides time, and it's unique up to isomorphism. It's very simple to see that is the case. It's a lot harder to show that nothing of order 0 mod 4 is maximal on its own. That's actually a bit of work. For orders that are 2 mod 4, we constructed maximal sets of size 5 and 17 using the extremes of the ones up here for order 6 and embedding them in larger structures. And this is somewhat notable because this 17 was considerably higher than anyone had even managed to build, regardless of maximality or not. So that was improving the bounds known there, given that we don't have a general construction in that case. Hadamard matrices won't save us. And we thought a bit about this function, which I'll call mu of n, which is the smallest k at which you can have k maximal mutual orthogonal frequency squares of order n. So I guess by the above, mu of n is 1 if and only if n is 2 mod 4. That's another way to phrase my first theorem there. And it turns out that we showed that mu of n is at least 3 in the other case. And this was an annoying amount of work. Like it really took it took many pages to prove that you can't have a maximal pair of mutual orthogonal frequency squares of order 0 mod 4. The other surprising thing is, given this, so we know there's lots of small maximal sets, there is no bound on this function. So Chairman Porrick, give me your favorite large integer. 2 to the 20 plus 2. Okay, so I can give you an n for which mu is greater than 2 to the 20 plus 2. If I make my n big enough, there will be no maximal sets smaller than 2 to the 20 plus 2. So your n in that case will have to be divisible by a very large factorial, so it'll be enormous. Yeah, 2 to the 20. I thought you might say that. Yes. Yeah, that's still true. Still true. So yeah, so you can get stuck at the first step if you're 2 mod 4. You can get stuck at the 9th step if you're 4 mod 8, and that series continues. But if you're divisible by a sufficiently high power of 2, we don't have an easy construction for a maximal set. But even more than that, we can show there are no small maximal sets if you're divisible by a very large factorial. So by a factorial of a large number, which is even worse. Okay. Yeah, well, absolutely. Wouldn't that be fascinating? Yeah. Yeah, okay. It's a comment now. Oh, so the comment was that he would love to have a similar thing for MUBs. Okay, for the people online. Okay, so I wanted to tell you a little bit about how we showed things were maximal. And it's a very simple idea. You take the Z2 sum of all your matrices and then hope that it's rank 1. So if you are lucky enough, or you construct your matrices well, then when you take the Z2 sum of everything, it will have this structure, and we say that it satisfies an R by S relation if that's the size of your matrix at the top of zeros. And the two MOFs that I gave you at the start actually satisfy a 2-0 relation. So I'm allowing R or S to be degenerate here. So here those left-hand blocks are degenerate, and I just get this rank 1 sum. And another example which will become relevant on the next slide is I could just start with a matrix with that 0, 1 pattern. So if I start with this matrix, it will satisfy an n onto by n onto relation. Okay, so why is that interesting? Well, we proved that if n is 2 mod 4 and it satisfies an RS relation, then and if the number of squares that you have in your set is odd, then necessarily both R and S will be odd, but probably more interestingly, the set is necessarily maximal. So there's a parity argument here that says if you have this condition on the sum of your matrices, then the result will be maximal. And then something interesting happened, which is that you can't have this condition satisfied if number of squares is 3 mod 4. It sort of looks like from the first theorem that you could, but you can't. So you can only do this for 1 mod 4. And this is starting to explain that gap that we saw for order 6, where we had maximal set of size 1, and the next one was size 5. Okay. So we did search for simple analogs of this in the 0 mod 4 case. We couldn't find any nice condition that just said, if you have this relation, then you'll be maximal. We do have some constructions for maximal squares there, and they do satisfy relations, but you need a lot of other stuff to be going right in order for it to be working. All of the largest sets for order 6 satisfy a 3-3 relation. So there's 18 non-isomorphic ways to get 17 MOFs of order 6. They all satisfy a 3-3 relation. So it sort of looks like maximality is all about relations, but unfortunately there are some maximal at the other end. There are some 5 MOFs that don't satisfy a relation, although they're very rare. Almost all of the sets do satisfy a relation, and so unnecessarily maximal because of the top. But sometimes you get something else like the identity matrix as your Z2 sum, which doesn't fit the theorem. Okay, and we conjecture that there are no maximal sets of any size of order 2, 3, or 4. Okay, so this gap that we saw for order 6 will persist. And we did prove this for 0 mod 4, and if it hadn't been so brutal, we would have proved it for 2 mod 4 as well, but that was going to be a really long paper, which we couldn't stomach. But it seems, well, we think this is true. Okay, so I need to start wrapping up. So I wanted just to connect to back to theme of the conference. The construction that I gave you for a complete set from a Hadamard matrix doesn't actually require, well, it requires the whole matrix if I want a complete set, but if I just want a set of MOFs, then you can just give me a Hadamard rectangle. So if you give me R rows that are orthogonal and +1, -1, that's what I mean by R by N Hadamard rectangle. And that will give me R-1 squared MOFs. And so my question is, if your Hadamard rectangle is maximal, does that imply anything about maximality for the MOFs? And I am guilty of not having explored this question very much at all before throwing it out there, but so I don't have very much to say in answer to it, but I think it's an interesting question. I'm just going to say a few things about what's known about Hadamard rectangles and maximality. So there's this nice theorem from 78 that if you get within 7 rows of the end, you can always get to the end. And I would love to know if a similar thing is true for the MOFs. I mean, it must be. I mean, so we have a theorem like this for moles. We were discussing possibilities of a theorem like this for MUBs this morning. I'm sure it's true for MOFs, but I don't know what the result is. It'd be nice to know what it is. I actually learned about this theorem from a paper of Rob and co-authors that gives some nice circulant maximal Hadamard rectangles in the paper, and also claimed a 5 by 12 maximal Hadamard rectangle, which is kind of interesting when you have a look at the theorem. But anyway, yes. Anyway, but you know, so there are some constructions out there is the point, and it would be nice to know if anything transfers from the Hadamard space to the Moff space. In this, there was a conjecture of Bieder who looked at the data for small orders and thought that all R by N maximal Hadamard rectangles would have to have R a multiple of 4, and that it wasn't possible to get anything non-trivial when n is a power of 2. And that's kind of deceptively what you might think if you look at the data up to say n is 12. But if you go a little bit further, then you soon discover that's not true. Anyway, so there are in some of these papers there are some constructions that would give you things which are verifiably maximal Hadamard rectangles. The question is whether any of those arguments transfer to maximal sets of Moffs, and I'll stop there.